Okay, so we are at the last breakout session for day one of Spring One 2021. Our next speaker is Mark Thomas from VMware. And the topic that Mark's going to talk about, I think, is useful for almost everybody or every application developer at least. Mark's going to talk to us about debugging complex issues in web applications. And I'm looking forward to this talk myself. So I'm going to hand it over to Mark without further ado.
Thank you very much. Welcome, everybody. Let's just get the screen sharing sorted. Okay, so I'm going to start with a quick introduction. My name is Mark Thomas. I've been a Tomcat committer for a while now, and since 2008, I've had a very simple job description. And that job description has always been go and do whatever you think is best for Apache Tomcat. So I've spent the majority of my time on the Tomcat mailing lists, posting as Mark T at apache.org, but you'll also find me contributing to other Apache projects such as Commons Daemon, Pool, and DBCP because they feed into Tomcat. And I'm also involved over at the Eclipse Foundation in work on the Jakarta EE specifications because those are the specifications that Tomcat implements. At VMware, I also help provide third-line support to customers that are using both Apache Tomcat and VMware TC Server, which is VMware's server that's built on top of Tomcat and adds various monitoring and management features. Before I get into the agenda, I do just need to show you the disclaimer slide. I'm sure you've all seen this multiple times already today, so I'll just give you a couple of seconds to remind yourselves of its content, and then we'll get on into the agenda. So what I want to cover today is, first of all, a little bit of background. So what do I mean by a complex issue, the methodology I use to approach them, and a little bit on statistics. The bulk of this session, I'm going to be talking about use cases, examples where we've had a complex issue that we've had to debug. The focus is probably going to be on the first two and not quite so much on the third one, simply because the third one's actually quite big. And if we did it in the same level of detail, we'd probably be here for another 3 or 4 hours. And I definitely get told off by the producer. After that, there's a few techniques around debugging these sorts of issues that aren't covered in the use cases. So I want to cover those. And then in terms of questions, we have another Zoom session after this that you're welcome to join if you have any questions. And there's also a Slack channel. So if you do think of a question in a couple of hours or a couple of days' time and you want to ask it, please feel free to join the Slack channel, ask your question there, and I will certainly do my best to answer it. So into the background then, and what do I mean by a complex issue? Well, this is naturally something that's going to be subjective. My idea of a complex issue might not be quite the same as yours, but for me, there are typically 3 factors I look for, and they're not completely independent, but it tends to be that one will dominate more than the other. And those 3 factors are these. First of all, any issue that isn't 100% repeatable. And generally, the harder something is to repeat, the harder it's going to be to debug. And the reason for that is that however you approach debugging issues, it's fundamentally going to be a case of recreate the issue, gather some data, analyze the data, do something, repeat. And if the issue isn't repeatable, that first recreate the issue bit is going to take time. And the harder it is to repeat, the more time you have to spend trying to recreate the issue. So it tends to just drag the process out. The second factor are issues that occur under load. And the main problem here is the sheer volume of data debugging those issues tends to generate. If you've got something that only shows up once or twice a day, when you're hammering the server with tens of thousands of requests, you're going to have an awful lot of application logs, debug logs, Wireshark traces, so network traces, lots and lots and lots of data. And you need to find the one request that went wrong in amongst all of that. And that takes time. The third issue is concurrency. And issues around concurrency tend to happen when you've got multiple threads that are interacting. And it's usually the case that the problem, whatever it is, only occurs when a particular sequence of events happens between those threads. And that sequencing is very timing dependent. And what can happen is as soon as you do anything to try and debug the issue, whether it's tweak a configuration, change the request slightly, maybe add some debug locking, that's enough to change the timing, which changes the triggering of the issue and perhaps makes it either you can't see it, or it's much more difficult to see. Sometimes if you're really lucky, you do something that makes it easier to recreate the issue, but it's usually the other way around. So if I see one of these three factors attached to a bug, that's when I tend to think, okay, this is going to be complex. And for me, that means something I'm going to need to sort of put a day or more aside to work on rather than an hour or two. Now, in terms of methodology, I think that the first thing to stress is whatever issue you're looking at, it needs to be sufficiently repeatable that whatever process that you're following is viable. And for me, if I can recreate it in sort of 20 minutes, half an hour, then that's enough that I can definitely tackle it. If it's more complex than that, then it's going to really slow down my the time it takes me to fix the issue, just because I can't afford to sit around for hours waiting for something to recreate. So you end up sort of setting a test up, letting it run, go and do something else, come back to it later. And that just naturally stretches the process out quite a lot. But assuming that this is something that does repeat often enough that you can sort of tackle it in one go, then broadly my approach is always the same. First step is to work out at a high level where the issue is occurring. Now, if I don't have much information, then it's going to be, well, it's somewhere between where Tomcat starts working on the request and where we see the issue, which is normally an exception or an error in the logs. So somewhere between starting the request and whatever code throws that exception, the issue is in there somewhere. The trick is to work out, exactly where and narrow it down. And the approach I take is I'll record the state before the area of code I'm interested in, record the state afterwards, and then for when the issue occurs, what I'm looking at is how has the state changed and how is it inconsistent? Then based on that inconsistency, what does that tell me about where that inconsistency occurred? And sometimes you can narrow things down quite quickly because you think, oh, well, if that variable has changed, the only place where that's written is there, so you can narrow down quite a bit. Sometimes it's rather more difficult. With the trickier issues, if I've still got quite a big block of code to look at, then I sometimes don't just record state before and after. I'll possibly record it at multiple points. So say I've got 5 points, record the state at all of those points, run the test, and then for the failed instance, look at, okay, is the state changes consistent between each of those points? And where does the change become inconsistent? Then I can narrow down on the code that's between those two logging points. With all of this, to sort of test whether or not the fix I've made has fixed the issue or whether I'm still seeing the issue, I'm really looking for some sort of binary test. Essentially, either it works as expected or as it doesn't. Now, that might be just a single test. Send a single request, get a result back, it either works or it doesn't. More often than not, though, it'll be some sort of small load test. So I'll run requests at the server for 5, 10, 20 minutes, and I'll either get a set of results that are all right, or I'll get one or more errors. So if they're all right, I consider the test to have passed. If I get one or more errors, then I consider the test to have failed. And that brings us nicely into statistics. Now, I am very much an engineer, not a mathematician. So this is very much coming from the sort of engineering estimate perspective of things. If you want to dig into the maths, then there are lots of resources online, and feel free. But for me, the engineering estimate is good enough for what the work I do. So the question I'm often trying to ask myself is, okay, I run the test 5 times and I get a failure once. I make a change, I run the test again another 5 times and I don't get any failures. Does that mean the change I made fixed the issue? Or does that just mean I'm observing some statistical variation? And with only 5 tests and 1 failure, I haven't got enough data. Now, I've been caught out by this many times when I think, oh yes, it failed 3 times out of 5 and now it hasn't failed at all, therefore I fixed it. And actually what I'm observing is sort of the extremes of statistical variation. So to avoid that, you most certainly need more samples than you think you do. And the 3 guiding principles are you need to have at least 20 tests, you need to have at least 5 of those passing, and you need to have at least 5 of those failing. If you don't meet any one of those, you need to do more tests until you meet all 3. Now, There is an obvious edge case there, and that is if you have genuinely fixed the issue, you're not going to see any failures. So at some point, you do need to make a judgment call and say, yes, okay, I haven't seen any failures for X tests, therefore I believe I have genuinely fixed this issue. One final point to note, and we will see this in the third use case. Sometimes it's rare, but it does happen. You can have multiple root causes or one issue that's masking another issue, and you fix the first one and then the second one becomes exposed. You do just need to be aware of that. So when you're running your tests, do keep an eye on what failures you're seeing, and is it the same failure? Is it different? Might there be multiple issues here? Just something to keep an eye on. As I say, it doesn't happen very often, but when it does, it can confuse matters if you're not sort of have at the back of your mind that that might happen. So do keep that in mind as you're working through these issues. And with that, we're going to go and look at some use cases. And I'm going to start with an example from the Tomcat users mailing list in June this year. If you want to look up the details, you can access the mailing list archives on that URL. And trouble with HTTP2 during bulk data transfer server to client, that's the title of that particular mailing thread. And this was an example of a nicely written bug report. And it boiled down to when the customer or the user had multiple streams, HTTP2 streams, writing on the same connection, sometimes they would all block indefinitely. Now, the blocking indefinitely worried me initially because that really shouldn't happen. But the user clarified that actually what they had was they configured an infinite timeout. So essentially, it was blocking until the connection timed out. And it was never timing out because they configured an infinite timeout. Okay, fair enough. So we haven't got some sort of infinite blocking because that would worry me. That was sort of user triggered by using that infinite timeout. So we've got streams that are all blocked, okay? And they provided us enough detail that we could recreate it. And essentially, the details were you need to be writing large files. And by large files, we're talking multiple gigabytes. And you needed 3 or more streams trying to do this all at once. They also said that they could recreate the issue with HTTP2, but they couldn't create it if they used HTTP 1.1. Now, that suggests quite strongly that whatever issue there is in the HTTP2 code, but it doesn't guarantee it. It could be that the HTTP2 code path has a particular timing issue that triggers something lower down in the stack that is actually shared across all HTTP connections. It's just that HTTP2 triggers the issue. So whilst I've got HTTP2 at the front of my mind, I'm not ruling out any of the other code at the moment. The users mentioned a couple of things they tried changing to see if that made any difference. They tried using the servlet non-blocking API as well as the blocking API, and that didn't make any difference. That's actually good news because writing good non-blocking code to the servlet API is hard, and debugging it is even harder. So knowing that it didn't matter whether we used non-blocking or blocking meant we could construct the test case with the blocking API and have both a simpler test case and a simpler task at debugging it. The other thing they'd done is they'd swapped out their file copy code for Tomcat's internal IO utils. Now, it's not unusual for file copy code to have bugs in it, but by swapping out for IO utils, we could be fairly sure that wasn't the case. And a quick look at their source code, I couldn't see anything wrong with it either. So it doesn't look like an application bug. It does very much look like a Tomcat bug at this point. They gave us all of the version numbers, and they also provided us a test case with source code. So we were able to start work on this very quickly. Additionally, they'd also done a little bit of analysis. And the analysis they'd done is they basically done a thread dump, and they could see that all of the threads that were blocked were all waiting for the same semaphore. And really, the only piece of information that was missing in this report was how easy this issue was to repeat. We asked them that question on the mailing list. They got back to us in less than an hour, and the answer was about 60% of the time. So 60% of requests would trigger the issue. So it's going to be relatively easy to debug, but because, or at least I thought it was going to be relatively easy to debug, but you've still got that factor of, well, it doesn't happen every time, even though you're sending it the same request. So there's something timing related of a sort in there. So we're going to have to dig into this a little bit more. In terms of looking at the relevant source code, HTTP2 connections are multiplexed. So what that means is you can have multiple streams where a stream represents both a request and the associated response, all trying to write to the same network connection at the same time. Now, because you don't want one frame from one stream intermingled with a frame from another stream, we have a semaphore to ensure that one writes at a time, and that's the semaphore that these streams were blocked on. Also, it's useful to know in this case that internally Tomcat is using asynchronous writes with a completion handler. What that means is if the write can't complete, the socket's added to the polar, and all of a sudden you've got quite a bit of state you need to manage. There's the completion handler, the polar, the socket, the HTTP2 connection, the stream, and keeping all of that together, we use internally this operation state instance, which goes in the write operation field. So essentially that's the state for the current write operation, and we'll refer back to that in a bit. So at this point, we've got a really good description of the problem. We've got a test case, and we were able to recreate the problem locally within about 90 minutes of the report being made to the mailing list. Now that's really quick, and it's a very good indicator that it was a quality bug report that we had here. And because we can recreate the issue, and because it happens about 60% of the time, it's fairly easy to start including, excluding functionality. So the first thing that Remy suggested, one of the other Tomcat committers, was let's try disabling the asynchronous I/O. So rather than using the internal asynchronous with the completion handler and everything, let's go back to normal synchronous I/O and see if the problem goes away. And it did. Now that does a couple of things. First of all, it tells us that the problem is almost certainly in the asynchronous I/O, so that narrows down where we need to look, but it also provided a workaround to the user. They could disable the asynchronous I/O, that's just a configuration option on the connector, and their immediate problem is solved. That did trigger a brief discussion on whether disabling asynchronous I/O would cause a performance issue or not. And the short answer is no, absolutely not, for the simple reason that the application at the moment is sending multiple large files on concurrent streams down HTTP2 connections, and that's horribly, horribly inefficient anyway. So the benefits or not of using asynchronous I/O are in the noise, and really nothing you need to worry about. As well as disabling asynchronous I/O, the other thing we were able to do was try testing one of the other connectors. And we tested with the NIO2 connector, and that wasn't affected by this issue. So at this point, we're pretty confident it's somewhere in the NIO asynchronous code that's used by HTTP2. So we've got a reasonably narrow bit of code to look at. Let's see if we can identify the root cause. We can see the threads are waiting for the semaphore, and we know by inspection that the semaphore should have been released by the polar, and now it hasn't been. Okay, let's start with a code review. And straight away, I spotted something that might be interesting. There was an interest ops flag on the socket, and it's non-volatile, but it's accessed for both read and write by multiple threads. Now, that could be a possible source of a threading issue. However, it's also possible that depending on what other fields are accessed, whether those fields are volatile, whether any sync blocks are used or not, it might actually not be an issue. Now, there are two options here. Option one is spend several hours very carefully analyzing the code and working out whether or not it's an issue. Well, there's option two, which is make it volatile, test it and see if it makes a difference. I went for option two because it was quicker. And initially, the testing was very positive, and I thought I'd actually fixed it. And I was getting to the point of writing the email saying, yep, solved it. And I was just running one more test, and then it failed. And then I remembered my statistics. I hadn't done enough testing. So I went back, did more testing, and it became obvious quite quickly that, yeah, no, the interest ops flag has absolutely nothing to do with this. Okay, set it back to non-volatile. Let's carry on with our work. Where to go next? Well, we can see that the semaphore hasn't been released. The semaphore should be released by the polar. So maybe there's something going wrong with the socket polar interactions. I mean, it's fairly complex code. There's multiple threads involved. If there's going to be a problem, some sort of edge case that's not quite handled properly, it's a reasonable possibility it's in there. So let's start debugging that. So that's what I did. And I hit a common problem with this sort of issue, is that as soon as I added my debug logging, so I had a bit of the code I was interested in, debug logging before, bit of code, debug logging after, check the state. Unfortunately, I couldn't, because as soon as I did that, the problem stopped happening. certainly in sort of 10 or 15 tests, I couldn't repeat it. And that's a problem because I need the logging information to tell me what's going on. But if the logging information means the test never fails, I don't get the information I need. So what I did was I changed my logging strategy a bit. And I used a trick I've used before, which is rather than generating a log message before, because generating log messages involves string concatenation, writing out to files, it's a relatively expensive thing to do. What I did was, okay, let's just copy the information I want to local variables, because that's nice and quick. Then let whatever the event is I'm interested in happen. And then afterwards, I'll log the before state, which from the local variables, and I'll log the after state. And because all of that expensive logging that slows things down and affects timing happens after the bit of code I'm interested in, it's much, much, much less likely to impact it. Essentially, it's only going to impact it if that copy of local variables takes up enough time, and it rarely does. It didn't in this case. I was able to use the logging effectively once I changed tactics. And the good and bad news is after an awful lot of debug logging, probably the best part of a day, my conclusion was actually the polar is working perfectly. Now that's good, because if the polar isn't working, all sorts of subtle bugs can happen. But the downside is we still haven't got to the root cause of this issue, what's going on. So next step, well, let's follow what happens next. The polar is signaling that the write was possible. So why isn't the semaphore being released? You know, it's literally 3 or 4 lines of code from A to B, and it's not happening. What's going wrong? So my next step was let's start tracing the write notification. And as soon as I did that, what was going on became a lot more obvious. When the polar tried to notify that the socket was ready for write, it looked up the operation state and it was null, which meant the event couldn't be processed. So the semaphore was never released. So the streams are all blocked. That's certainly a big step in the right direction, but it doesn't tell me why the operation state was null. So I went back to code review, what accesses operation state, how could this turn out to be null? And then certainly a potential root cause became obvious. I applied what looked, but assuming the root cause was correct, I applied the fix, local testing confirmed it. I was able to explain on the mailing list what happens. That meant one of the other committers could check my reasoning, they concurred. And I also took the time to check whether or not the error could happen elsewhere. And because read and write are so similar, we had exactly the same bug in the read code as well, just nobody had ever stumbled across it. So we were able to fix that at the same time. Now, if you want to understand actually what was going wrong, it'll help if you've got the code in front of you, although it's not strictly necessary. It's all in socket wrapper base. You need the write, which is in line 13, and I can't quite read underneath the that will pop out that's got all my video on it. Apologies for that. And the completion handler, which is a 1044, I think it's 1360 something, but it's pretty obvious to find in the code. So 1366, there we go, I was right. So what's going on? Let's imagine we've got 2 streams. Each stream uses a thread, we'll call them thread 1 and thread 2, and they both want to write to the connection at exactly the same time. So they both try and get the semaphore. Let's say thread 1 wins. So thread 1's got the right semaphore. It starts its write, so it creates its operation state, sets that to write operation, starts its write, completes its write. The completion handler is called. The completion handler releases the semaphore, at which point thread 2 that's still waiting for the semaphore says, great, I can start writing now. So thread 2 starts its write process. So it creates its operation state, it sets the write operation, and it starts to write to the network. Meanwhile, thread 1's completion handler continues, and it gets to the point where it says, yes, I wrote something to my operation state to write operation, didn't I? I better go and clean that up. So it goes and nulls it out. The problem is what it's just nulled out is actually thread 2's operation state, not its own operation state. And that fundamentally was the bug. Meanwhile, thread 2 doesn't notice this. The write continues. For whatever reason, the write doesn't complete. So the socket's added to the polar. Once the socket buffers have cleared, the polar signals the socket's ready for write. It goes to look up the write operation to get the operation state, finds it's null, so it can't notify the operation state, it can't notify the semaphore, does a normal dispatch, essentially just ignores the event, so the async write times out. And the fix is really simple. When the completion handler is processing, it needs to clear the operation state first and then release the semaphore. That way, whichever thread is waiting for the semaphore, when it creates its operation state, the current thread isn't going to then overwrite it. And there's the commit for that one. End to end, I think, if memory serves me correctly, that hit the mailing list about lunchtime on the first day, and it was all fixed by the end of the second day. So that one was fixed pretty quickly. This second use case, somewhat different, took about 6 weeks beginning to end on this one. And the main reason for that is that I never had access to the system where the issue could be created. I was never able to create the issue locally. It was all this work was done on the mailing list with just some logs that contained sensitive data sent to me directly, but all the bulk of the work was all on the mailing list, essentially all remotely like that. So let's start with the original report. It's again on the Tomcat users mailing list back in October last year. Great subject line, weirdest Tomcat behavior ever. Sort of subject line makes you think, yeah, I think they're sort of over-egging it a bit. But actually, once I dug into the issue, I tend to agree with them. And again, it was a well-written bug report. It didn't actually give us much detail about the bug, but it did tell us a lot of what they'd already tried and the investigation they'd done. And that is just as helpful. And the bug report was really as simple as very occasionally, Tomcat doesn't send a response. So as the bug reports go on its own, that's not much use, but it was all the extra information that was. So they told us that the access logs showed that there was a response. There were no errors, exceptions, or anything in any of Tomcat's logs. They had a Wireshark trace of the connection to Tomcat, and that showed a GET request followed by a TCP FIN packet. That's essentially indicating a clean TCP close. And they provided all of the version information. And really their question was, well, where do we go from here? This doesn't make much sense. So where we went from there was, well, okay, let's ask them a few more questions. Let's try and narrow down where things might be happening, what might be happening. So the first question was, how big's the response? It's only a K. That's interesting, because if a response is that small, there are all sorts of points in the network where the response could be fully buffered. And depending on when the response gets to a point and when another point times out, you can actually get those crossing over and effectively the response will be dropped. Maybe that's happening. That theory was destroyed by the answer to the next question, which said the typical response time was 60 milliseconds. Well, that means it's pretty much not going to be timeout related. Looking at the Wireshark traces told us that actually the TCP FIN was sent about 100 microseconds after the request was received. Well, that definitely rules out anything timeout related. So it's not that. That made me think, well, okay, if Tomcat's closing the connection that quickly, that normally means there's something wrong with the request. Now, it would be unusual for Tomcat not to send a 400 response, but if the request is so badly formatted, Tomcat can't be sure it's an HTTP request, it won't send an HTTP response. So maybe the request is malformed. Look at the Wireshark logs. No. The request was absolutely perfect. The headers were valid. The request body, when it was present, was correct. The content length was correct. Any chunked encoding was correct. There was absolutely nothing wrong with the request at all. So that wasn't it. And architecturally, they were able to tell us it was user agent to firewall to Nginx to Tomcat. That might have been more interesting if we were looking at the timeout side of things, but we weren't. So we sort of filed that information away for referring back to later if we needed to. Digging into the Wireshark traces a bit more, we could see that it was an HTTP 1.0 request that was failing. That at least means we can rule out all of the HTTP 2 code. So that's a chunk of code where we know the problem isn't. But equally, the HTTP 1.0 code is some of the oldest code in Tomcat. It's some of the most well-tested, most robust. So it's really unusual that an HTTP 1.0 request is failing like this. Yeah, it is definitely a weird issue. In terms of network traces, we had the trace from both the Tomcat and the Nginx side of the connection. What that meant was that we could rule out any strange network effects, like it's a dodgy network cable, or there's a piece of network equipment dropping packets, or anything like that. Because we had the traces at both ends and we could see that the same thing was happening at both ends, we could rule out all of that, which was great, but still not that helpful in terms of getting us towards a root cause. The application did have unique request IDs. That definitely helped with log correlation. So when we're looking at Wireshark and access logs and the debug logs, being able to pull out that request ID was very helpful. At this point, I did ask the user, how do you feel about deploying some custom debug code to your production instance to gather some more debug logs? And they said, well, we could. It's not ideal, but yeah, we could. We'll consider it if we need to. So we sort of put that in our back pocket to come back to if we needed to. I asked the obvious question, when did the issue start and what configuration changes happened at the time? About a month ago, no configuration changes. And it's worth asking that question. But I think in all honesty, in about 15 years of doing this sort of thing, I think I've had the answer once. Oh, about 3 months ago, just after we made a configuration change, and the configuration change is the cause of the issue. Doesn't happen very often, but I guess it's a question you have to ask. We noted that the systems were likely loaded, only getting about 20 requests a second, and given that Tomcat will handle orders of magnitude more than that, it didn't seem to be sort of load related. At this point, one of the other users on the mailing list said, why don't you try using strace? Now, the original reporter, the OP of the issue, didn't see that suggestion. I did, but I thought, that's a bit too low level, really. It's an operating system debugging tool, really, more than a Tomcat one. I mean, maybe, but not yet. In hindsight, yeah, that was the way we were going to find the answer. So we could have saved some time if we'd followed that, but in reality, it wasn't sort of where the percentages were. So we carried on for the moment. So what we tried next was, well, let's try some configuration changes. So if we change from the BIO connector to the NIO connector, does it make any difference? No, it didn't. Okay, so that rules out anything in Tomcat's BIO and NIO specific code. It also rules out, or at least makes it a lot less likely, anything in the JVM. And the reason for that is the BIO and the NIO code in the JVM are very different. So if the issue happens with both, it's probably not a JVM issue. The timings we could see in the various logs suggested that the JSP, which was the target of these failing requests, was generating the response. Just to be sure, we added %b to the access log configuration. That records the number of bytes written to the response. And that confirmed that, yes, as far as Tomcat's concerned, yeah, those bytes were written. So this is now really strange. Just sort of recapping other things we know, because it happens with BIO, we know it's not send file, so that's more code we can rule out because BIO doesn't support send file. There isn't any compression involved, so there's no gzip, so any of the compression code, that's not a factor, we can rule that out. There really isn't any obvious explanation at this point. So we are back to that, yeah, okay, we're going to need to run some custom debug code. So that's what we did. Version 1 was fairly simple. It confirmed that, yes, the application did write the response. Yes, the socket was closed before the application wrote the response, and the correct objects were used. That last point was just checking a bug that I do see fairly often in applications, which is where a request tries to write the response to an output stream associated with a previous request, and generally bad things happen. But that wasn't happening in this case. All the correct objects were being used, so that was all good. So the next version of the debug logging, we tried to gather a little bit more detail on when things were happening and who's closing the socket. So I actually, at this point, I'd wrapped the socket close method and I was basically logging any calls to it. And what we saw was that the socket was closed way before Tomcat tried to write, and neither Tomcat nor the application was closing the socket. So what on earth is closing the socket? Take a quick look at the JVM source code, and there's nothing obvious there where the socket would be closed that isn't triggered by a call to socket.close, and we already know that that wasn't being made. So what on earth is going on? That brings us to debug logging version 3, where I sort of take the view that, right, something odd's going on with this socket. I don't know what. So I'm going to wrap the socket, and I'm going to log the parameters of every single method call. I'm going to log the return value of every single method call, and I'm going to put a try catch block around the entire method and catch any exceptions, and then log them. What that got us was we were seeing an exception on write, an IO exception with message bad file descriptor. Now, my first reaction was surprised. I said, well, why on earth didn't that appear in the debug logs? Yes, there are places where we swallow IO exceptions, but we log them on debug, so you don't miss things like this. So I went looking at the Tomcat code and I found a problem. The problem was that the point where the exception was happening was at a place where we saw lots and lots and lots of IO exceptions due to the clients just dropping the connection. So we just ignored the exception. That was a mistake. We should have been logging it at debug level, so it was available in situations like this. So the Tomcat was changed to log all such exceptions now at debug level, and all versions of Tomcat do that going forward. We had the exception now. Now, bad file description normally means the socket's been closed. Well, we kind of knew that, but might it mean we're running out of file descriptors? So we checked how sort of the file descriptors, kept a running track of how many there were and what the limits was, and we were nowhere near the limit, so it wasn't that. Debug logging version 4 was me sort of exploring the theory that, well, is one request and response interfering with another one? Is some other request, this request is behaving correctly, but is some other request sort of stomping on the socket and closing it? However, what debug logging version 4 showed us was that we would still see the issue when there was only a single active connection, i.e. the one that went wrong between Nginx and Tomcat. So it's not some sort of request response interaction issue. At this point, I'm quite stumped. I'm not quite grasping at straws, but I'm not far off. Thinking back in time, and I'm a long way back to the days of Java 1.3, 1.4, there were bugs in the JRE where it mishandled file descriptors. So might that be what we're seeing here? To investigate that, we did some very invasive reflection, went right deep down into the JRE source code to find the file descriptors and log them and check that they were correct all the way through. And they were. There's really no sign of what was going wrong. So it's at this point, I'm thinking, okay, now's the time for strace. Something somewhere is closing this socket. What is it? It's not Tomcat. It's not the app. I don't think it's the JVM. Right. What does strace tell us? And the first strace showed us that actually the socket close was coming from the JVM, which is like, well, what on earth calling it? It's not Tomcat. It's not the app. How's this happening? So our first idea was to, well, let's try capturing some thread dumps at the point we detect the error and see if we can see if there's any other code that's messing about with sockets. That wasn't particularly successful. It kind of relies on the thread dumps being generated very quickly after the error happening, which isn't always the case. And we did have a few false leads. We thought it might have been database related, but a bit more digging showed that that wasn't the case. Eventually, after a few iterations with strace configuration, we got to the point where we basically told strace, log absolutely everything to do with file descriptors. Now that generated quite a big log, but we were able to work through it, align the timestamps, and then we were able to see what was happening. And by going further back in strace just to trace how the problematic file descriptor was used, what we could see was there was actually a native library within the application that wasn't managing file descriptors correctly after a fork. It was essentially closing the same file descriptor twice. So what would happen is it would close it the first time correctly, that's fine. The file descriptor goes back in the pool. Shortly afterwards, a new connection arrives. That file descriptor gets allocated to the socket. Tomcat reads data from the socket, starts processing the response. Meanwhile, the native library then closes it a second time. That closes the network connection. Tomcat doesn't notice because it hasn't used it yet. As soon as Tomcat tries to write the response, that's when it finds that the network connection has been closed and you get the bad file descriptor. All in all, that took us about 6 weeks to get to. Initially, the vendor was adamant that it wasn't their application, but they really couldn't disagree with all the logging. Literally, we could see step by step. You could see the DLL closing the file descriptor once, closing it a second time, and it all going wrong from there. So once they were presented with the evidence, then yeah, they said, fair enough, that's a problem. It was actually a problem in a library called PDF-tron, which was from yet another vendor. So what the application vendor did was provided some instructions on how to disable the use of the library in that particular instance. And we recommended that, well, actually, if you switch from HTTP 1.0 to HTTP 1.1, you'll use a persistent connection between Tomcat and Nginx. And what that means is because you've got a persistent connection, you're not constantly changing the file descriptor, so there's much less likely that the native library is going to have the same one and then close it on you. So between that, I think the user was still seeing a small number of issues, which we think were to do with other uses of PDF-TRON that hadn't been disabled. But the user was going to go away and talk to the supplier about that, and they haven't come back since. So I'm guessing that's what the issue was. Right, so I want to, as I said at the beginning, I want to go through this third use case a little bit more quickly. And that's because it was one of these where multiple things were going on. So I just want to sort of use it as an example of the sorts of things that to look for and how to work out when to sort of hand the baton over, as it were. So this actually originated on Spring Framework's issue tracker, January this year. This also took about 6 weeks or so to work through to a conclusion. And the description of the issue is response writing fails to complete with webflux on Tomcat. Essentially, they were getting some form of exception when they're trying to write the response. Another well-written bug report came with a test case. There were a relatively small number of failures under load. They did provide all the version information, and the biggest issue with this was repeatability. I found that at various points with this particular issue, I was having to swap from different operating systems to try and recreate it. Sometimes it would recreate more easily on Linux, sometimes on Windows, sometimes on Mac OS. It was very timing sensitive. And it was one of these cases where there are actually multiple problems found. And Rosson and I were doing a bit of a tag team on this. So the initial issue was that Spring wasn't handling failed flushes as well as it could. So Rosson fixed that, ran the test again, and then when the errors came up, it became fairly obvious there was something wasn't right with Tomcat's error handling. Excuse me. And as I looked into it, what I saw was actually 3 separate problems. The first was that if an error occurred during the processing of the error page, that error would overwrite the original error that was being processed, which meant when you're trying to look at the logs, you didn't have the original error. So that was a simple fix. Right, let's not overwrite that. Let's keep the original error and report that one. First issue fixed. Having done that, the number of errors went down. We could see what was going on. And what became apparent was that errors were happening during a call to onWrite possible, which is one of the non-blocking I/O listeners in the Servlet API. It's a method onWrite listener. But I/O exceptions were happening in that method, but it wasn't triggering the error handler. And the reason for that was that the error handler wasn't properly set up in time for the very first call to onWrite possible. So we fixed that. That got us a bit more information, able to move on. Still seeing errors, and it was still a bit messy, not as clean as we would hope. And again, debugging our way through the error handling, looking at what was called when. What was realized was that in onWrite possible, and obviously the application is writing, and there may well be an I/O exception during that. Tomcat assumed any I/O exceptions would be rethrown, either wouldn't be caught, or if they were caught, would be rethrown. So effectively, Tomcat, the method calling onWrite possible, would see that exception. However, webflux was actually swallowing them. Perfectly legitimate. The servlet spec says nothing about whether those exceptions should be swallowed or not. So webflux was well within spec to do what it was doing. Tomcat was making an assumption that wasn't valid. So we had to correct that. Fortunately, because it was Tomcat that was actually triggering the original exception at a lower level, it was very easy just to set a flag that Tomcat could check later on to see whether an exception had happened. So having fixed all of that, we seem to be at the point where, okay, we're not seeing a Tomcat error, we're seeing what looks like a Spring error. So baton back to you, Rosson, and see what you can find. So he did some more work and improved the handling in Spring around broken pipes. And that then highlighted another problem with Tomcat's error handling. Now we're narrowing down the frequency that these things were going wrong, but we were still seeing problems. And what was happening here, there were times when the error listener was being called and everything worked perfectly. There were other times when the error listener was called and it didn't have all the information you'd expect it to have. And what was happening was, in some cases, Tomcat was handling the error internally and doing some cleanup before the error listener had a chance to deal with the problem. So we swapped that around, that fixed that. We're still seeing the issue occasionally. I thought it was a Spring bug. So again, I handed it back to Ross and he took another look and said, no, don't think so. I think something weird going on with Tomcat. I spent quite a bit of time digging into it. And what I eventually found was that for one incoming connection, we were getting 2 firings of the socket accept method. And there should really be, it should absolutely be a one-to-one mapping. Because there were two firings of socket accept, it essentially meant we had 2 threads trying to process the same socket, and that's never going to end well. That looked very much like a JDK bug, so we reported that to the JDK team. They very quickly got back to it. Actually, it's happening, even though we're down, it's happening at the OS, and they provided some C code that demonstrated it, so that we actually ended up with it being reported as a bug in Linux's network stack to the Ubuntu team, and that's currently where the issue sits. I don't believe they've really started looking at it yet, which, and if anybody knows a way of prodding that team to take a look at what's definitely a bug, I'd appreciate it. Do let me know in the Q&A or the Slack channel afterwards. So I said after the use cases, I wanted to talk about a few techniques that I haven't mentioned. I have talked a lot about using logging and using Wireshark. One of the techniques that's really useful, particularly with bugs that are hard to repeat, is rather than keeping gigabytes upon gigabytes, hours, days even of logs, use a 5-minute rolling window. What I find works quite well is having 5 log files, each of a minute long, and then they just roll them over as you need to. Then when the bug happens, all you need to do is copy those 5 log files, and you've got 5 minutes of data to wade through rather than 5 hours or more. And you pretty much, 5 minutes is plenty of time to gather everything that's going on between the error. At least it certainly has been in my experience. You can always make that a bit longer if you need to. So by using that rolling window, you have a much smaller log file to work with. It generally makes your life a lot easier trying to find a particular set of data that relates to when it went wrong. If you're adding custom logging to try and track what's going on, I typically just log it immediately at error level. 2 reasons for that. One, it means I don't need to change Tomcat's default logging to see the messages in the logs. And 2, if I log them at debug level, A, I'd have to change the configuration, and B, I'd get all of the other debug messages as well, and I don't want those. I just want my specific ones, so logging them at error level lets me do that. Occasionally, you'll have an issue that depends on network latency. These days, it's very easy to simulate in the hypervisor. In the past, I've done things like running Tomcat on a cloud instance to try and get some latency between the client and the server. But nowadays, I just do simulate that in your hypervisor of choice. Load generators are often problematic. Certainly, my recent experience with HTTP2 load generators is that they're not always completely spec compliant. They don't always behave the way you think they do, and their error handling can sometimes be very, very poor. So just be careful when you're using a load generator and you're seeing strange results. It might be the load generator. Certainly in my experience, it's just as likely to be the load generator as it is either the application or Tomcat. So be very careful with that. Make sure it really is doing what you think it's doing and it's behaving properly. I have found when I've had any sort of error that's to do with a drop network connection, the only way I can simulate it is with 2 physical machines and pulling out the network cable. Anything else I've tried, whether that's killing the browser process, just turning the Wi-Fi off on the laptop, pausing the VM, anything, doesn't seem to work because somewhere says, there's an in-progress network connection. And you've just something to close it down. Let me close it down cleanly for you, which of course is exactly what you don't want, and then you can never recreate the issue. So for anything around issues with lost connections, 2 machines, pull out the network cable, much more reliable. A final comment on multiple platforms. I've mentioned a few times in this session that the OS I've used has sometimes changed the timing and made an issue easier, harder to repeat. I've certainly found that moving between OSs. I've never found that when moving between bare metal and a VM. In my experience, if I can reproduce it on any OS, Linux, Windows, Mac OS, if I can reproduce it on that, I can reproduce it both in a VM and on bare metal. That difference really makes very doesn't seem to make any difference at all in terms of reproducibility. The thing that does make the difference is moving to different OSs. As I said, that last Spring issue, I was bouncing between different OSs at different points, trying to improve the reproducibility so I could make some progress debugging the issue. And with that, that brings us to the end of the session and questions. So there is another Zoom session set up for questions. I'll be over there shortly. If you do think of a question after that session is finished, don't forget we've also got the Slack channel as well. I'll be keeping an eye on that for the next few days and weeks. Any questions you think of after the event, please feel free to ask them there and I will do my best to answer them. Other than that, thank you very much for your attention and I hope to see you in the Q&A.
All right, thanks, Mark. That was great. And that is a wrap for the breakout sessions for day one. We do have a full day of sessions tomorrow, so be sure to join. And also, we're not yet done with day one. Round two of the main stage presentations will be starting in just a few minutes, so definitely head on over there. And yeah, thank you, and hope you had a great first day.